Hello guys, welcome to the series on a practical approach to design and implementation of a PID controller. In this video, we will learn how to tune a PID with the help of a transfer function. In the previous video, we have seen how to convert a step response model into a transfer function. So now we will go on to the Simulink MATLAB environment. So this is the MATLAB Simulink environment. So now I will get the transfer function into the Simulink environment. So in the previous video what we have done is we have saved the transfer function as a TF1. So you can see over here, and the numerator and denominator of the transfer function is in over here. So now I will go to the Simulink and I will type transfer function, and you can get a transfer function block. So here I have got the transfer function block. Now I will open the transfer function block and update its numerator and denominator. So I will type in as the same order. Yeah, I will press apply and OK. Now if I enlarge this, I will be able to see my transfer function. So now what I will do is I will add a PID controller. So we have got the PID controller. Yeah. Now I will make the necessary connections. So over here I define a set point, that is the temperature at which I want to maintain my heater at. So this is a error detector which subtracts the set point and the feedback of the existing temperature. So here I get the existing room temperature. So these two value gets subtracted and I get an error signal which is fed into a PID controller. And this PID controller does some calculation and outputs an input value between 0 to, I'm sorry, it's 255. So it outputs a value between 0 to 255, which is nothing but PWM signal value, and this value gets into our hardware unit. So here the hardware unit is nothing but a transfer function, and the output of this hardware unit will be temperature. This temperature will be fed back into the error detector again. So this loop continues until we reach a steady state temperature, which is nothing but a 60 degrees Celsius in our case. So we have to tune our PID so that we get to this steady state temperature at a most efficient way. So for this what I will do is I will open the PID controller, and so you can have it as any type as you want. For now we will go with PID and it's a continuous time, and these three variables we are going to tune. So we are not going to tune it manually, but with the help of automated tuning. So this is a transfer function based PID tuner. So if I click on this tune button, PID tuner app will open. So before that I will put the output saturation constraints. So the upper limit is 255 and the lower limit is 0, and we'll add up a anti wind up method. Now I'll go and click apply, and now I will go and click on the tune button in order to tune the PID values.
So a PID tuner pops up. So this is a PID tuner app made by MATLAB.
So here I can see the response of the system for a step input. So I apply a step input of 1, and the response of the system, that is the output of the system. So this is the dotted one is before tuning of the PID, and this one is after tuning the PID with the PID constants. So I can change these curve by changing the behavior of the plant. So if I want it to be much faster, I can keep it on the extreme end. but here I have a overshoot, so maybe I will reduce that. And if I want my controller to be robust, I will keep it on this side. So based on requirements you can tune it. So I think this is much better for me for my applications. So what I will do is I will go and click on update model. So on bottom you can see the PID values, and here it says the PID gain applied to the block and the block response is updated. So now here you can see the updated block response. So now when you apply a step input to the system, this is how the output of your system is going to be. At around 400 to 450 you are going to achieve a steady state. So now I'll close this. So here you can see the PID tuned values. So these values are being tuned by the PID tuner app. So now the PID is tuned, so I'll go and click OK. So here the PID that we have is tuned. So now what I will do is I will run this model. So like I will check how the system approaches a 60-degree set point. So I have run this model. Now I'll click on this temperature, and you can see at around 400 to 500, that is at around 500 degrees 500 seconds, the system reaches a steady state value of 60 degrees. Here there is a bit of overshoot, but that is fine. So you can tune the PID controller to avoid any overshoots. So now I will close this. Now I will show you how to implement this PID controller on our real hardware. For that what I will do is I will open the PID implementation. So here I have a model. So instead of the transfer function, I have the real hardware model. So what I do is I give an input to the digital pin 9, which controls the heater, and from the analog pin 1 I get the temperature value. So that is the system input. The system input is nothing but a PWM signal, and the output that I get is a temperature signal. So this PID is being replaced by the tuned one. So here I have tuned a PID. So I will copy this and I will paste it over here. So this is nothing, this PID implementation is nothing but same as this one, but instead of a transfer function I have the exact model. So this is the exact hardware that I am going to implement it on. So now the system is tuned. Now I am going to test it on the real hardware.
I will show you a time lapse of the temperature input. Yeah.
The system has reached a steady state at around 400 seconds, and it has reached 50 degrees Celsius, and it is maintaining. So I think I will give some disturbance to the system. And here you can see there is a drop in the voltage and a surge in the input in order to compensate for the drop. So this means that our PID is well tuned, and it responds to the external disturbance in a very well manner. So here you can see there is a spike in the heater input, and it gradually decreases as the output temperature reaches a steady state, the set point. So this is the output of PID tuned response. So I think we can stop the simulation here. Yep. So also you can add a transfer function to the system, and you can see the correlation between the transfer function model and the real hardware unit. So I will show you how to add the transfer function. So I am going to use the same transfer function as we have used before.
So the input to the transfer function will be the input of the PID. So I will use a sum block.
So transfer function initial conditions are 0. That means our room temperature is 27, but the transfer function doesn't know our room temperature and it assumes to be 0. So what I am doing is I am adding the room temperature to the output of the transfer function. So you can run this model to find the correlation between the transfer function and the real hardware unit. I have already run this model and I have got the output over here. So let me zoom. So this is the output of the transfer function on the top. The blue one is the output of the transfer function temperature, and the bottom one is the output of the real hardware unit. So I think we have come to the end of this series. So in this series we have seen a practical approach to design and tuning of the PID controller, and I guess we have successfully done it. So hope you like this video series, and thanks for watching. All the files and all these has been attached in the link, and the MATLAB files are available in the MATLAB file exchange. All the links will be put in the description, and thanks for watching. Have a nice day.